Hi everyone, Kurt with Hypnodyne. Today we're going to take a look at the spectrogram. The spectrogram is simply a picture. It's a colorful picture that is used to visualize a signal. Now, most people are familiar with the traditional time-based way of visualizing a signal, that is, to have the time on the x dimension and some kind of value of the signal on the y dimension. So if you're looking at waves, for example, this period from a slow wave sleep, in particular N3 sleep, you see a signal that's going up and down and up and down. Now, the exact value of the signal at every time point doesn't really tell you much about the signal. So a long time ago, some smart people have figured out, hey, why don't we represent a signal using time versus frequency instead of time versus value. And that's what the spectrogram is. It's a representation of time versus frequency. Let's see how it works. First of all, in the x dimension, we still have time, so that's unchanged. Now, if you're using HDScorer, this HDScorer software, for convenience, the way that I've laid it out is that you're seeing one epoch here, but you're seeing the whole night on the spectrogram, so that you can use it as a map. You can click on any portion of the night and see what that looked like below, right? So you have the whole night here. This is the beginning of the night, and that's the end. That's on the x-axis. Now the y-axis is the frequency, with the top part being the lowest frequencies. For example, here we have this nice yellow band, and that yellow band represents low frequency alpha waves. See this activity where the signal is going up and down and up and down about once a second. That is what's creating this nice yellow band here at the top. Then we have another band about 1/3 of the way down, and this other band is created by sleep spindles. Now we'll see all about that. We'll see what sleep spindles are and how to recognize them. But if you just want a quick preview, that's this guy right here, and this one here, and this one here, and this one here, and this one here. See this very frequent spindle activity lasting anywhere from 1 to 3 seconds every time. That's what's creating this band. Now, the advantage of looking at the spectrogram is that you don't need to move from epoch to epoch, figuring out what stage is this, what stage is this. But just by looking at the spectrogram, you know that there's spindle activity from right about here to right about here. This nice chunk, this is all spindle activity. And when you zoom out a little bit more and you look at the night in its entirety, you see that there are 4 rough sleep cycles, because every sleep cycle has its slow wave sleep segment, and during slow wave sleep is when you always have sleep spindles. So let's say cycle 1 from here to here, cycle 2 from roughly here to roughly here, cycle number 3, and cycle number 4. So this is one way in which the spectrogram helps you to see what's going on and look at the night in its entirety. Another way in which it helps you is the following. Movements, or generally anything that disturbs the EEG electrodes, results in a bright vertical line. For example, let's move here and see what's going on. Here we have a lot of movement, you can see here in green, and consequently the EEG signal becomes very dirty. It goes out of range for some 4 seconds. So that's what's creating this vertical line. Now, if you were going through the epochs, you would have to examine each epoch individually, but if you just look at the spectrogram, you can see that there's a vertical line here, there's another one here, there's another one here, there are a couple here, there's another one here, and so on and so forth. And you can get a feeling for, you can immediately get a feeling for the quality of sleep of the patient, just based on how many times they moved around. And you know that, for example, from this point in time to this point, there was roughly no movement. So that's a good chunk of restful sleep right there that didn't have movements. Now, of course, the patient could be completely still, that is, not move around at all and still be awake, but most of the time, If the person is not moving and you're not seeing these vertical lines, that means, let's just say sleep is going well on that particular night. Now, if we want to see a little bit more detail, we can actually switch to the X-ray. Now, the X-ray is a way to change the spectrogram and highlight certain features that I've developed. And as you can see, the spindle chunks that I've shown you before become a lot clearer. I'm going to go back and forth a couple of times so you can see the difference here. You can see that all the vertical lines have been removed, and also all the noise associated with patient movement prior to going asleep, that's also being removed. Now, the most important thing that the X-ray does for you is highlight very weak activity. What do I mean by that? Well, we've already seen that this is a chunk of slow wave sleep that has very strong spindle activity, right? But you could have seen the spindle activity also looking at the signal, like look here, for example, and here. On the other hand, here you can see some very faint alpha activity that is not immediately evident by looking at the signal. Alpha activity, as you can see, is, well, let me first of all highlight it because it is very faint. It's right here. Now, being this faint, it's very hard to see if you look at the signal like this. And in frequency, if we talk about frequencies, the standard alpha frequency is about 10 hertz, and the standard sleep spindle frequency is about 12 hertz. Now, that's not always the case, but for most people it is. And in this case, it checks out. So that's why the alpha, if you can even see it, it is really faint, but it's slightly above the spindle frequency. Now, in the normal spectrogram, it would have been very difficult to realize that there's something hidden in there. It just looks like part of this huge vertical type noise occurring prior to the patient settling down. But if you move to the X-ray, you can actually see. And you have to look for this specifically at the beginning of the recording. Why is that? Well, alpha activity is associated with wake. But it's not always the case that if you're awake, you will have alpha frequency. Alphas begin to be seen when a patient closes his or her eyes and is generally quiet and not trying to engage in some demanding mental activity, let's say. So if you're doing neurofeedback, for example, I have another video where I'm showing using ZMax connected to BrainBay, which is a neurofeedback software, a neurofeedback and biofeedback software. And what I do in that video is connect the alpha waves to some music. So the music begins to play louder if I'm able to create alpha waves. So to get the music to play a little bit louder and not go silent every few seconds, I have to close my eyes, first of all. And then I have to sort of space out with my mind in such a way that I'm not really thinking about anything. But all of this is very tangential to the basic point, which is that if you're trying to score sleep, many times you will see this little itsy bitsy alpha thing, and it's going to occur right before the patient falls asleep. It's not going to occur throughout the whole wake period, because evidently here it's all wake. And at the end also we have all wake. This happens to be a study in which the patient remained awake for a while. After waking, they stayed on the bed for a while. So that's why we have this portion of the recording. If you were recording this by yourself, you'd probably switch off the device at this point once you've woken up. But for this study, what actually happened is that the patient was instructed to just remain in bed and, do whatever. So I was just pointing out the fact that this whole chunk of wake and this whole chunk of wake, that doesn't have alpha. But this tiny bit after the person settles down, and by the way, let's also correlate that with the movements. As you see here, the patient is still moving around. Look at how much movement in the green section. And then they're trying to settle down, moving again, settling down again, moving again. And once they settle down for good, now we have this nice and flat green signal. And here's when alphas start to show. Or, well, start not to show on the signal, but you can see them in the spectrogram. So the X-ray of the spectrogram, to sum up this last tangent that I've set out on, the X-ray allows you to see weak activity. And here we have an alpha. So I've already shown you one horizontal band of sleep spindles that was already clear in the spectrogram. Now I've shown you another band of horizontal activity. Sorry, another horizontal band of activity that is alpha for this particular subject that actually wasn't so easily visible in the spectrogram. You don't have to worry because there aren't many of these. There's, there's sleep spindles, there's alphas, but for the most part, that's it. Now you might be wondering what this is, and when you get to this high frequency activity, it's probably something from grinding teeth or clenching teeth. It's some high frequency activity that could come from eyelid flutter, something like that. You don't really need to worry about what's going on the lower half of the spectrogram. What you really care about is the spindles and if you can spot any alpha. Now, if you can spot any alpha, it's nice because alpha at some point decays. For example, I would put a marker here that alpha is over right here. Do you see that there's like a hole in between alpha and spindles? That's N1 sleep. This is the time in between alphas decaying completely and the onset of slow wave sleep. When people are awakened during N1 sleep, they report that they weren't sleeping at all when in fact they were not conscious. I guess the way that we realize that we were sleeping is we are able to introspect on our short-term memory, and when we find that, hey, short-term memory doesn't contain anything at all, that's something odd here, I probably was sleeping. Well, during N1, it's quite likely that actually that short-term memory didn't get wiped out, and so didn't get wiped out yet, and so you don't really have that feeling like you were sleeping, but you were. The patient is unconscious at this point. All right, no problem. So we've analyzed, perhaps I went into a little bit more detail than I wanted to, but that's probably it as far as what the spectrogram can show you. And let's recap. So horizontal bands at about 12 hertz that repeat with each sleep cycle. These are the sleep spindles indicating slow wave sleep activity. Then we've got this alpha activity right here, if you can spot it. Now, some people don't have it at all, and some people have it very strong, and some people actually have two bands stacked on top of each other. So people vary, and some people have alpha at the same frequency as spindles, but that's very, very rare. But, and some people don't have it at all. For some people, you won't see any alpha here, and that's fine too. Now, it's reported that about 87% of people have alpha on the frontal leads while falling asleep, and remaining people, let's say like 13% don't. But I think that because most recordings are actually scored using this type of signal and not looking at the spectrogram, it's likely that this is slightly underreported. So for instance, if a sleep technologist were to look at these epochs here, they would probably not report this person as an alpha producer, or frontal alpha producer is how they're called, because there's very little to see right here. But fortunately with ZMax, we're able to see that, and this helps us to know that up until this point, the patient was actually awake, and from here to here, we have N1 sleep, and from here onwards is N2 sleep. So without even looking at what's going on here below, just from the spectrogram, I've already pretty much scored at least up to here, this chunk. Because slow wave sleep starts with N2 sleep, then it goes into N3 sleep. It doesn't matter. I know that at least up to this point, it's probably N2 sleep. So I've already scored this much just by looking at the spectrogram. So the spectrogram is a very useful tool. It also, let's say you're scoring sleep here on HDScorer, it allows you to go back and forth between different sleep cycles and figure out if there are any differences, or if there's one epoch where you're not really sure whether it's N2 or N3, you can say, okay, well, I'm gonna go back to the first cycle and see what N2 looked like in the first cycle. But this is if you really want to split hair. There's one last thing I'd like to mention about the spectrogram. I've told you how vertical lines represent movement, artifacts, distortions, electrode problems and all of that. But there are some types of vertical lines that, I probably should have a better name for them, but they are kind of vertical lines, but they're fading out towards the end. And I mean like this section here. I don't know if you can see that this vertical line is very bright up to the very bottom. This one too, this one too, this one too. But these two look like vertical lines, but they're sort of fading halfway through. And let's see if we have more, like here, also fading halfway through. There's another one here that's fading. And then there are some that don't even get to halfway, like this one and this one. What are those? And by the way, you can't see them on the X-ray. You can only see them in the regular spectrogram. You're supposed to go back and forth between the two, really, to get a good picture of what's going on. But these are actually eye movements, very, very often. Let's look at them. Now, I don't want to start talking about this signal right here because this is a whole different topic for another video. But if you've ever seen EOG, that is electrooculogram data before, you know that this kind of anticorrelated activity does indicate eye movements. But already from the spectrogram, you can sort of see eye movements. Now, it's not 100% of the times that these things are eye movements, but I would say at least 90% of the times they are eye movements, especially if you can see that they're happening in groups and they're happening in between bands of sleep spindles. So the way that I look at this night is I know that the patient sort of fell asleep right here because this is where all the noise ends, all the, broad spectrum kind of light color activity ends. I know that they probably woke up again right about here because there's a lot of, color here. There's a lot of high intensity interference type stuff here. And then I know that there were 4 sleep cycles from these 4 horizontal bands. I know that the sleep got interrupted here a bit because you see the spindles disappearing and then reappearing again. I can see that the body was sort of trying to go back to slow wave sleep but couldn't. Because you see this dot. That was trying to form another horizontal band but couldn't. And here again. And here again. And then finally it went back into slow wave sleep. Normally you see these kinds of things at the end of the night where the sleep pressure has decreased and the body oscillates quite quickly between sleep stages. But in this case, I guess you could say in a way to look at this is the brain wasn't really sure whether it should stay in REM sleep or go back and do another sleep cycle. You could see it like that. And, I call these gaps between the sleep spindle bands, I call them holes very often, or gaps. But if you see these kinds of, let's call them vertical lines disappearing throughout the spectrogram that is not having light color until the very bottom. If you see them occurring at the gaps, especially if you see multiple ones, that's nearly always eye movement. Okay? So already from the spectrogram, I saw when the patient went to sleep. I saw when they woke up. I can see how many cycles there were. I can see what the sleep spindles look like. I can see they're very bright and intense. I can see where the gaps are, and I can even get a moderate amount of confidence as to where the eye movements occurred. And of course, eye movements are occurring during sleep in the REM phase. That is when the person is actually dreaming, and the eye movements in the dream and the eye movements that the body actually makes that can be recorded are identical. So I can see that activity. Now, just to give you an example of something that was not an eye movement, but still leaves that sort of a vertical band that's disappearing throughout half of the recording, you can see something here. I don't know exactly what it is. It looks like eyelid flutter. Sometimes create this kind of really fast, M shape. What do you want to describe this? That's not very important, but the spectrogram doesn't give you all the information. Otherwise, there wouldn't even be a signal below, right? So in this case, I'm able to move here and say, was that eye movements? Yes, that was eye movements. And then I move through here, thinking that since it occurs around a gap or the center of a gap, that's probably an eye movement as well. However, when I look at it, I realize that doesn't look like an eye movement. That's something else. Okay, so you need to then, of course, corroborate your theory with the actual signal. But as I said, in 99% of the cases, like I'm almost sure there's an eye movement here. There you go. I'm almost sure there's another one here. And I'm almost sure that there is another one right here. So there are some. Okay, that's, I think, a basic introduction to the spectrogram. Thanks for watching, and I'll see you next time.